You're right. Okay, welcome everybody again. We just started recording. This is actually class 4B. We're talking about another class. One of you guys is sitting in it, where I made several mistakes in that class. The first one was an algebra mistake that led to a tremendous error that we could immediately pick up, okay? And we went through it 3-4 times and we couldn't find the error. After the class was over, I went back and I found that there was a step. Instead of dividing, I multiplied, and that led to the error. So making an error is a human. I mean, doing errors, that's human, that's normal. What is actually nice, what is actually important in the process is knowing you have made a mistake and walking yourself steps basically backward to try to find where the mistake was. That is actually powerful stuff. That is a skill that you really need to develop. Recognizing when you have made a mistake, hopefully to catch it before it goes further. And even if it goes anywhere, you're going to basically come back and know that the error, that there was a mistake. So that is important. There was another problem also in the rush of things. And because that's still kind of bothering me at that point, I made another mistake. And that mistake clearly led to some nonsense results. Because we plugged the two, there was two linear equations, basically we plugged them on the calculator, and it gave us some nonsense mistakes. If you guys took physics 4C, basically the specific heat must be positive no matter what. So we ended up with one that is negative, so we know that terrible. And then there was another mistake also in the same calculation, in part of the same result, which is the fact that the specific heat was, another value of the specific heat was higher than that of the water, which is also a mistake. So that we caught it immediately in the class. So we went back and I found that basically instead of taking the difference in the temperature, I took one temperature. So again, making a mistake is a human. That is fine. I mean, anybody can and does mistakes. Knowing that you have made a mistake, that is a skill you need to really develop from all of these problem sessions that we do together, okay? And walking yourself backward, trying to fix it, that is actually even better, okay? So that's why I'm not ashamed, first of all, and nobody should, that you make mistakes. Nobody is really that smart to begin with, no matter who you think that person is. And what is important, like I said, is having that skill, which is very, very important, okay? So that's what you should really be proud of. Here is the problem with the first class also that happened in the morning. There was a major disruption also on Canvas again, and not on Canvas, on Zoom again, okay? So if there is a disruption right in the middle of class, please do not leave, okay? For some reason, last semester it was happening on Tuesdays. This semester it's happening with the class, this specific class, the one that happens in the morning, where Harris is sitting in that class, okay? So don't leave. Give me a chance. I will come back to you guys, and then we close the class normally, basically after we finish everything we are supposed to do. So for you guys, we promised a bunch of problems. So let me go back into my notes and then share with you the screen. Okay. Okay, what is that thing there? And where is my share? This one. So we have a bunch of problems that we promised to do. I think problem 1 is this one, no? We promised to do problem 1. Okay. In another setting, in another class, let me first of all add in here, this is chapter 24 problems. Okay. So the problems again are problems 1, 51, 53, 57, and 59. Problems 1, 50, did I say 53? No, 51 first. 53, 57, and 59. Okay, there are 1, 2, 3, 4, 5 problems. Okay, it's from this chapter. Okay, one of you guys from another class actually mentioned something which is very, very important, and you're going to see it today. Okay, you will see often for the charge, it's appended to it either the micro, the nano, and sometimes even the pico, either coulomb, coulomb, coulomb. Okay. You'll also see the capacitance appended to it, the letters either micro, nano, and pico, microfarad, nanofarad, or picofarad. Okay. This one is 10 to the power -6. This one is 10 to the -9. And this one is 10 to the -12. Sometimes you even have a femto, like the lab, okay? Which is 10 to the -15, okay? Because these things are very small. Having 1 coulomb charge is too much. That's why you don't deal with that much things. You don't run in the street to 1 coulomb. You can't. It's too much of a charge. So that's why this unit's in there. In solving the problems, though, do not be tempted. Resist that temptation of appending the powers. Leave that to the end. You may cancel the micro and the micro in here, and all of a sudden you're dealing with simple numbers, okay? So resist the temptation to plug in these powers. You may be safe just to leave it as is, okay, until toward the end. So that was really the note, and it's an important one, okay? Okay, so let's do problem 1. Okay, so problem 1, again, because it's important for the lab, actually, problem 1, and it's important because you really need to know how to plug in numbers, because you're dealing with capacitors. You can make one actually yourself, but you need to know how much capacitance you actually built in that one. Okay, so it says the plates of a parallel plate capacitor are 2.5 millimeter apart. You see, now we're talking numbers. So we have a plate in here and a plate in here. So this is a cross section A. You can make it probably with aluminum foil in your kitchen. And you separate them with a distance of 2.5 millimeter. So this is your D, okay? And think of those one as aluminum foil that you have from the kitchen. You can go and grab. Each one of them has an 80 nanocoulomb. So there is a Q in here, 80 nanocoulomb. All you have to do is grab a balloon or this pen or anything made out of plastic, rub it against something, and tap it on the screen of the make it on the on the aluminum foil, and now you have 80 nanocoulomb in there. Okay, and there is actually, similar to the first lab, you can actually do it in such a way both of them have the same charge, except the other one will have a -80 nanocoulomb on it, and that's it. And now you have a capacitor. You built yourself a capacitor in the kitchen. Okay. The plates are in vacuum, air, it's the same thing. The electric field between the plates has a magnitude of 4 volts. The electric field, 4 volts, 4 million volts per meter. Okay, how can you make that in the lab? Connect them to a battery, basically, okay? Now you have yourself a capacitor with charges. Actually, you don't need to rub anything with anything. You can use the capacitor in this case. You can use a battery in this case, the 1.4 volt battery to dump the charges on this thing. And that's it. You have now a capacitor. Okay. Now, what is the potential difference? So we have, first of all, E. That is E, which is equal to 4 mega volt per meter. Okay. 4 times 10 to the power 6 volts per meter. Remember, I made a note on this fact that the electric field from this point on, instead of using the unit Newton per coulomb, which is fine, Now we're going to be using volt per meter. It's a better, more practical way of using it, because you have distances in meters, albeit this distance is in millimeter, and you have the volts, which is coming from your battery or something. So this is a more practical way of measuring things, and instead of having to think of a coulomb being carried with you all the time, and actually a spring attached to a system in here to measure the forces. Now think of it as just volts per meter. Okay, it's the same thing. Okay, so this is the unit we're going to be using for the rest of the class in here, for the rest of the semester, for the voltage, for the electric field. So they gave us the electric field, and they asked specifically what is the potential. The potential, if you guys remember, is the integral of E over space, but we have the voltage in here between, we have the electric field is constant in here. So when you integrate it, it's simply going to be the electric field times the distance. So it's simply just plug in the numbers, that's all. So it's 4 times 10 to the power 6 times 2.55, 10 to the negative 3. 10 to the negative 3 and 10 to the power 6, that's 10 to the positive 6. 4 times 2.5, that's another 10. So it's V is 10,000 volts. Make sense? That's how much. So a battery of 1.45 volts is not going to work. So you need tremendous amounts of voltage. See how much charge you have? You have nanocoulombs, 80 nanocoulombs, and this is how much voltage you have in there. There's tremendous voltage in there, 10,000 volts. Okay. B, the area of between the plates. Now we need to find the area between the plates. I know, so this is A. B now. The area between the plates is such a way that E is equal to sigma over epsilon naught. And that we know E is given 4 times 10 to the power 6. And sigma is Q divided by A. Sigma is the charge Q divided by the area A. So now we have everything. So we have E equals to Q over A times epsilon naught. From here, we should be able to find what A is. A is simply going to be the area of the foil that makes all of this thing work. Aluminum foil is going to be Q over epsilon naught times the electric field. So Q is 80 nanocoulomb. Now I need an area in meters, so it's really, I have to do the numbers now. I can't really say leave the N in there. So it's 10 to the negative 9, okay? That is how much E is. I mean, that much Q is. Divided by E. E, as they gave us it to be equal to 4 million. That's 4 times 10 to the power 6 for the electric field. Now I need epsilon naught. I know 1 over 4 pi epsilon naught is 9 times 10 to the power 9 in SI. So all I need to do is multiply by 4 pi and divide by 4 pi. If I divide by 4 pi, I have 9 times 10 to the power 9. Now I need to divide, I need to multiply by 4 pi. In other words, epsilon naught is simply equal to 4 pi times 9 times 10 to the power 9. So that is, 1 over epsilon naught. I'm sorry, did I say that? 1 over epsilon naught is this number. So epsilon naught is a lot smaller number, so it's the inverse of this number. So 1 over epsilon naught is a big number. So times 4 pi. So now I plug in everything into a calculator, and you should be able to find what this thing is. So the calculator, 80 divided by 4 is, of course, this is, I need to make some simplification. That is 20. And 10 to the power 6 and 10 to the power 9, that is 10 to the power 3. So at least we have so far this number is in here. So let's get this numerator and numerator only. So what I have 20 times 10 to the power negative 9. I really should handle that power too. Let's leave the power by itself. Okay, it's going to be 10 to the negative 6 anyway. So it's going to be a very small area in there. Okay, and it's going to be in square meters. So the area is going to be in square meters. So 20 times 9 times 4 pi. And that's all there is to it. So 20 times 9 times 4 pi, it's 2,261 times 10 to the negative 6, because so if you want to, so it's 2.26 times 10 to the negative 3 cubic meters, okay? So that, square meters, I'm sorry. You guys need to correct me on these things, okay? So this is how much it is, or if you like, it's 22.6 centimeters squared, okay? Because a centimeter is a hundredth of a meter, but you have two of them in the square, so it's 22.6 centimeters squared. Make sense?
Yep,
yes, no?
sense.
Okay. So, I mean, aluminum foil, how much is it going to be? Is it going to be really that big? It's 22 centimeters. So if it's 1 centimeter on one side, it's 20 centimeters on the other side. If it's 3 centimeters on one side, 7 centimeters on the other side, and so on and so forth, okay? So you can do the square root of this and find the number for it. So it's going to be a little over 4, less than 5 centimeters side by side. So you're looking at something, it's a good idea to visualize this when you're doing practical numbers, okay? You're looking at 5 centimeters on each side, roughly 4.5, 4. So this is how the physical size of it in here. I have a ruler in here. So this is the size that we're talking about, okay? So this is basically how much squared, of course. This is a square if you take the square root of that. So this is the area of the aluminum foil, okay? And the capacitance, now we're ready to do C. Okay, since we have Q and V, we really don't need to use a formula, but we have two ways of finding C now. One way is using it as C is equal to A epsilon naught divided by D, or C is equal to Q over V. Whichever way you want to do, it's the same thing, okay? Because you have V, you have Q. So this is going to give me 80 nano coulomb divided by the voltage. And the voltage, if you guys remember, was 10,000 volts. So it's 10 to the power 10 times 10 to the power 3 volts. So if I use these numbers correctly, the nano is 10 to the negative 9. And 10 to the positive, basically 3, so it's going to be 10 to the negative 12. And 80 divided by 10, that's 8. So this answer is going to be 8 picofarad. Okay? Because this is a 10 to the negative 9, but then I have to divide it by 1,000, so it's going to be promoted to 10 to the negative 12. So it's an 8. 80 divided by 10 is 8. Okay? So it's 8 picofarad. This should also give me 8 picofarad. Remember, the area is some number 22.6 or 2.26 times 10 to the negative 3 times epsilon naught. Epsilon naught is that the invert of that number divided by D, and D was 2.25. Or 2.5, I'm sorry, millimeter. So this was 2.5 times 10 to the negative 3. And now I have to plug in the value of epsilon naught, which is 4 pi times 9 times 10 to the power 9. So if I do that, I should find the same number. Please verify it. So there are two ways of finding C now. See, this is one way for you to check if you did a mistake or not. Make sense? So let me try to see what I get from there. 2.26 divided by 2.5 times 4 pi, 4 times pi times 9 times 10 to the power 9. I get 7.99 times 10 to the power negative 12 farads, or 7.99 picofarad. Does it make sense to you guys? Yes, no, maybe?
Yeah,
So there
makes
were
sense.
two ways. Very good. There were two ways to make how to find C in this case. Either you use the formula for the parallel capacitor, which is A epsilon naught over D, and that gave me 7.99. The reason why it gave me that number is because this number is not precise. 2.26 was just a rounded number in here, okay? Times 10 to the negative 3. I cancel 10 to the negative 3 with 10 to the negative 3 in my calculator. So I did 2.26 divided by 2.5 times 4 pi in the denominator. That's the value of epsilon naught, by the way. It's 1 over, okay? And then 9 times 10 to the power 9. So when you plug this number, I get this much. But then I know also it's Q over V. And we just found V to be 10,000. And we know Q is 80 nanocoulombs. The only problem is I have a nano divided by 1,000, which is a pico, okay? And 80 divided by 10. So this is actually much faster to find the answer. But it's still, both of them should match. And they do within the basically rounding issues. So hopefully this problem... I'm sorry, Sarah, were you saying something?
No, I was just going to say it makes sense.
Okay, very good. So basically, this problem hopefully was an appetizer for you guys. Now we get into the main course, okay? Problem 51. So problem 51, which is typical problems, that may be exam problems, okay? All of this stuff in here is important. Students tend to like very much circuits. When we get into this part of the course, they enjoy it so much. And hopefully you too, okay? Because this is really fun stuff in a sense. You're dealing with circuits and stuff like that. But then after that, we're going to delve back into the integrals and the stuff that most of students hate, okay? But part of the beast, what can we do, okay? Sorry about that, okay? So we have a point A. Next to it, there is a capacitor that is 8.6 microfarads. And then next to that, there was a 4.8 microfarads. Okay, don't put the powers yet, okay? Leave everything the way it is right now. Then there is a junction. In the junction, we have on one side, 2 capacitors in series. One of them was 6.2 microfarads, and the other one is 11.8 microfarads. Then on the bottom one too, there was 2 of them. No, there is only 1 of them. And then we connect them together again. So this one is actually 3.5 microfarads. And now this is point A, and this is point B. Okay? And they tell you that potential between across A and B is 12 volt. So VAB is 12 volt. VAB is 12 volt. That we know for a fact. That's what they said in the problem. Okay? Find A, the total energy stored in the network. How much energy is stored in the network? Okay. For that, I need to take this entire circuit and replace it by another one, actually. Leave A by itself and leave B by itself. And replace everything with just one capacitor, which is C equivalent. Okay. If I can find C equivalent, which is an if, okay, we have to find it first. then we know how much voltage is across this one. We know what C equivalent is this one. And if you go back to the notes that we did a long time ago, we found the energy to be Q squared over 2C. And I argued that that's an important thing somewhere in here. Q squared over 2C. But remember, Q and V are related to one another too. That V is equal to Q over C. So which means that Q is equal to VC or CV. So when you square Q, it's going to be C squared, V squared, and the C squared in the numerator cancel the C. So this 2, you can write it as 1 over C times V squared. So you can write it in terms of the charge, or you can write it in terms of the potential. When you write it in charge, you divide by C. When you write it in terms of the potential, you multiply by C. And this is because of this is how we defined actually the capacitance. Okay. So now let's go back to our problem. If I can find C equivalent, then I can find what the energy stored, because they ask us the total energy stored in the network. So total energy is going to be 1/2 of this C equivalent, if we find, times this voltage squared times 144. So basically all we need to do is find the equivalent capacitors. As a general rule, and it's very, very important when you're solving problems with electricity in general, not just with this problem, okay? When you're trying to find C equivalent or any equivalent of whatever, you go to the innermost. Okay, you go to the lowest point first, to the most inside. And the most inside configuration are 2 things. I have this ones that happen to be in series. Find their C equivalent, their own C equivalent between just these 2. And also, these 2 are actually in series too. Find their innermost C equivalent. Once I do that, then I'm going to combine this, because then that is the next level of this 2, the new C equivalent between these 2, combined with this one, but they're in parallel. And once I find that, now I found everything, basically, where this C equivalent between these 2 and this C equivalent between these 2 parallel ones is going to be my entire C equivalent. Okay, so let's do that. So between the 6.2 microfarads and the 8.2 microfarad, I have a 1 first C equivalent. Okay, so I'm going to call that C1 equivalent. Okay. So the C1 equivalent the first one, okay, is in such a way I invert the 6.2 and the 11.8 and add the inverses and then invert the answer. So it's going to be 1 over 6.2 plus 1 over 11.8, and then to the -1. The answer is going to be in a micro, is it micro? Yeah, it's microfarad. So I don't really bother with those powers of 10. That was my note earlier from one of the students in another place, that this is very important. Do not plug in that 10 to the -6. It's a waste of time. And it's going to basically, you're going to be prone to make mistakes. Just ignore it for right now. The answer is going to be in microfarads. First, you add the inverses because they're in series. That's why. So they're in series. That's why you're doing that. Okay. And then invert the answer. So basically, if I plug this one on a calculator, obviously 6.2. Okay, if I plug this one on a calculator, it's going to be, first of all, you're going to write the fact that this whole thing is inverted. So it's 1 over 6.2 plus 1 over 11.8. Please verify my algebra in here, okay? It's very important. To the power -1. And the answer is 4.06 or 4.1 microfarad, okay? So that's the whole answer in here. That is the answer between just the inner 2. Then I'm going to call this one C2, the other blue. That is between 8.6 and 4.8. So I need to find that one too. So C2 is also there in series. It's the same reason. C2 is actually equal to 1 over 8.6 and 4.8. So 1 over 8.6 plus 1 over. I assume that you guys have a piece of paper and you're actually doing this stuff, okay? Because we are not going to proceed if you're watching me do these things. And the answer is going to be in microfarads. Everybody's a microfarad, so the answer is going to be in microfarad. Okay, so I don't have to bother with that. So all I have to do is just plug in the numbers as they are, and then append the unit at the end. So the fact that there is a 10 to the negative 6, it's already there in this symbol in here. So again, open parentheses, 1 over 8.6 plus 1 over. If you don't believe I make mistakes in the class, just ask one of you guys. Today it was a disaster in the first class. A disaster in the sense there were a lot of mistakes, but it's actually an outstanding thing in terms of how to find them. To the negative, which was actually a positive thing. So this is 3.8, 3.08 that is, which is roughly about 3.1 microfarad, okay? I know I'm rounding up, so hopefully you guys will fix these things. So we found this C equivalent. So this is, I called it C1 equivalent. Did I call them C1 or C2? No, this was C2 actually equivalent. And this one was C1 equivalent. So this is actually C2 equivalent. And this was actually C1 equivalent. This turned out to be 4.1 and this one to be 3.1. Okay. Now, I need to deal with this thing in here, which I'm going to call C3 equivalent, which is just the sum of these two C's. Remember, because they're in series, they're in parallel, I'm sorry. So in this case, C3 equivalent is going to be the C1 equivalent plus this number, 3.5. So the 3.5 microfarad. So the answer is obviously 4.1 plus 3.5. And then I append my units at the end. I have 6 in here. And I have 9.6 microfarads. 7. 3.4 is 7, not 9. Sorry about that. Hopefully you guys are doing it right, not relying on what I'm doing. It seems like I'm completely all over the place today. So now the C equivalent for everything is the 3 equivalent. The 3 equivalent is everything in here, by the way. It's this guy. It's the green one. That is the C equivalent, 3, okay? And now this one is the C2 equivalent. So now this basically is going to give me the final answer. So the C equivalent now that I need is going to be 1 over the C3 equivalent, this configuration where things are looks like they're in parallel, plus 1 over C2 equivalent, where the two things were actually in series and I combined them, and the whole thing to the negative 1 power. And again, the answer is going to be in microfarads, okay? So now we're in business. So this one is 1 over 7.6 plus 1 over, how much was it? 3.1. And the answer is going to be in microfarads. So C equivalent is going to be equal to, again, I need the calculator here quickly. So it's going to be 1 over 7.6 plus 1 over 3.1. And the whole thing is to the negative 1 power. So it's 2.2 microfarads. I made a big fuss in the lecture, if you guys remember, about the fact that when they are in series, it's smaller than both of them. When they're in parallel, it's larger than both of them. But you cannot really go by this one right now because some in series, some in parallel. So you can't really say, oh man, we have, what is it? The smallest one is 3.5 and this one is 2.2. Therefore, this is justified. No. This does not mean that. You have to look at that rule for side by side. The 8.6 and the 4.8, when you compare them to find their C equivalent, it's 3.1. That is fine. Okay, that is justified in there. These two, since they are in series, 6.2 and 11.8, the answer must be less than the smallest, which is 6.2. And the answer is sure enough 4.1. So that makes sense. The 4.1 now and the 3.5, the answer should be more than the largest of the two, which is the 4.1. And sure enough, that was 7.6. Okay? But the final answer in here, you cannot compare it to all of the capacitances in there because the circuit now is all over the place. Okay? So make sure you pay attention to that, okay? So the fact that we found 2.2 microfarads, it looks like it's smaller than anything in the circuit, but that doesn't mean much. Okay? You might end up with a value that is more than 3.5 because again, the whole circuit is kind of all over the place, okay? So now we have found C equivalent. So the question was to find the energy. The energy is easy now. U for the entire energy is equal to 1/2 of the C equivalent that we just found times V squared. And now the 1/2 times 2.2 times 144, which is 12 squared. So the answer is going to be, and the answer is going to be in microjoules, by the way, because we left this guy in microfarads, okay? So that's easy. So 2.2 times 12 squared divided by 2. And the answer is 158 microjoules. Make sense?
Looks good.
Okay, if you guys understand, thank you very much, Jason. If you guys understand this thing, I think you're in good shape. Honestly, okay? You need to be methodic when it comes to this kind of circuits. You really need to go step by step. You cannot skip a step, and that's when mistakes happen. When you start to think, oh man, I grouped this one in my head, and then, okay? So, and then the second question was, and which is a typical question, the energy stored in the 4.8 microfarad capacitor. So they want the energy right here. Okay. They want the energy there for the they don't care about everything else. They care about that capacitor, okay? They want the energy there. Obviously, if I know the voltage between this capacitor and this capacitor only, I can multiply it by 1/2 times 4.8, and I'm in business. Or, if I don't know the voltage, I can find the charge. If I know the charge, it's 1/2 of Q squared over that 4.8 microfarads. So one of the two will do. Since I know now the equivalent capacitor, I know the charge actually that is sitting on this side of the capacitor and the charge that is sitting on the other side of this from A to B, basically, everywhere, okay? And that charge must be the same charge sitting on the 4.8 capacitor because it's on this side of the 8.6, and this one is going to be the negative value of that one. So this one must be that same charge. So now I know this charge, which is the same charge on this both sides. So ignore about this side, and here let's focus on this charge. So all we need to do is find that charge. So let's find the charge now in this C equivalent. Because we know the voltage, which is 12 volt, since we know VAB, and that is equal to Q, this very same Q, the Q total, if you want to call it the Q total, divided by C equivalent. From here, we can find what that Q total is, which is just the C equivalent times VAB. So that Q, the reason why I'm calling it Q total, because at some point it splits. When it finds a junction like this one, it's going to split into two parts. Part of it is going to go up and part of it is going to be down, and it recombines back to its own value. So in here, it's the same value for these two capacitors. The 8.6 and the 4.8 will have the same value. So now that's what I'm interested in because I want it across the 4.8 microvolt. Had the question was to find the energy stored in the 6.8, the 6.2, or the 11.8, or the 3.5. I really need to dig further to find what that charge is. So it's a good thing they didn't ask us that. They just asked one of these two, which is easy. Once we found one, we found the other, okay? So Q total in this case is going to be C equivalent times the whole voltage from A to B. Because this is how it looks like to me. It looks to me like there is only one capacitor of C equivalent with this voltage across 12 volts sitting across it. So now C equivalent, we found it to be 2.2, if you guys remember. 2.2 microfarads times 12, and 12 times 2.2 is what? 24 plus 2.4. So it's going to be 26.2, 26.4. 12 times 2.2. Yeah, 26.4. Microcoulomb. Notice the micro in here. I'm not doing that 10 to the power -6 to a nonsense stuff. I know somebody tells me, okay, this is not in scientific notation. It needs to be 2.64 times 10 to the -7. Ignore the scientific notation for right now. Just stick to the units, okay? You have a micro, leave it micro. So the answer is 26.4. The same thing actually happened in here, 158 microjoules. Now, what do you think the answer need to be for this energy stored in this capacitor? Is it more or less than 158 microjoules? 158 microjoules, remember, is the entire energy between end to end. So is this number going to be more or less than 158 microjoules? What do you guys think? We're looking at only this element from the entire configuration. Everywhere we found 158 microjoules. I want to know, do you think we will have more or less for this one? What do you guys suspect?
Less, maybe.
That is how it should work. So I know if I found it to be exactly equal to 158, I have a problem, because that means I have no energy stored in the other capacitors. Why? We need to ask why, okay? Why no charge reached the other capacitors? That's one question. If I found it more, I know for sure I made a mistake. So I need to go back and find where I made a mistake somewhere, okay? So that is exactly how the thinking I want you guys to be thinking, okay? You want to really have that upfront attitude to the problem. Okay. So the energy stored now in the 4.8 is simply equal to 1/2 of the charge, total charge scored, total charge, because that's the same charge on that capacitor, divided by the C of that capacitor. So it's going to be 1/2 of 26.4 squared, microcoulomb squared, if you like, divided by the capacitance, and the capacitance is 4.8 microfarads. 4.8, that is. Okay, the micro and the micro squared will cancel, and I will be left with a micro coulomb squared over farad squared, and that's going to be joule. So the answer is going to be a microjoule of some sort, okay? So the units are microjoule. We know that. So I didn't have to bother with that 10 to the -6 anywhere, even for this case for the energy, because the micro squared and the micro in the denominator will be left with just one micro. And here it is. Well, the Coulomb squared over Farad squared, that must be a joule. So let's leave that joule. Okay, so it's microjoules. Now I have to do 26.4 squared divided by 2 times 4.8. That number better be less than 158. If it is more, that means we made a mistake again, which is not out of the realm of the possibility. So 26.4 squared divided by, open parentheses, 2 times 4.8, and close the parentheses. Okay, the answer is 72.6 microjoules. Does this make sense to me? Can I accept this number, or should I go back and redo things? Okay, Martin thinks it's acceptable. Does everybody else agree with Martin?
Yeah, I agree.
Yep.
Okay, yeah, because it's less than 158. It doesn't mean it's right, but at least it's not wrong. Okay, that's what this means. So that means we're okay when we're doing problems like this one. Try to see, does it make sense? I think it makes sense at this point. Okay, there is nothing to be alarmed with. So probably, I mean, it looks like it's half the energy is stored just in this capacitor. If you look back into the circuit, which kind of something that you have to think about, why is that? Almost half of the energy is here. Okay, in this capacitor. So the other guys must have split the other half basically between them. The 80 microjoules or so that is left is split between everybody else. So that is kind of something that you probably need to check. If I'm doing this problem and if I'm taking this class honestly, I will calculate the energy here and here and here and here and add it up and see if it adds up to 158. That would be fun, and I think you should do that. You guys understand? So it's easy to find the next energy for this 8.6. For the 8.6, it's straightforward. All you have to do is just take that 26.4 microjoules, micro coulomb, square it and divide it by 2 times 8.6. So that is going to give you the energy stored in this capacitor, okay? The 8.6. Now here, you have to do some honest work to find out the energy is. You know the overall voltage is 12 volt. Now you know the charge in here. So you need to find the voltage drop in this section. The voltage drop in this section should be just the 12 volt. I'm sorry, should be just, we have the C equivalent in here too, actually. We have the C equivalent in here for that section to being 3.1 microfarads. Okay, good. 3.1 microfarads. And I know the charge is 26.4, so I can find what the voltage drop in this section only. This voltage drop, which should be just the charge, which is 26.4 microcoulomb, divided by the 3.1 microfarad. So this voltage drop, by the way, this is outside of the question, but I want you guys to start thinking proactively in this kind of problems. So the micro cancel the micro and the coulomb over the farad, that's a volt. So I have to do 26.4 divided by 3.1. Again, this is another problem that you have to be looking for. The overall voltage drop from end to end is 12 volt. So do you think this voltage drop is more or less than 12 volt? What do you guys think? I mean, before doing any numbers, is it going to be more than 12 volts?
No.
It has to be less too, because think that you have a battery that provides the maximum 12 volts. So how could you end up with something more than 12 volt in here? There must be another battery somewhere else. So if this voltage from A to B is 12 volt, this better be less than that. Okay, it cannot be more than 12 volts. So whatever it is, it's less. So let's find exactly how much it is. You have the charge over the capacitance. The equivalent capacitance was 3.1, and the charge for both of them, it's the same one, which is 26.4. So it's 26.4 divided by 3.1. Remember, the micro and the micro cancel. So it's 8.5 volt. So there is a drop of voltage in here between this node, this junction, and A of 8.5 volt. Which I can ask you now, how much voltage drop between this junction and B? If overall is 12 volt, and just this portion is 8.5. So how much do I have voltage drop between this junction and this point B?
3.5.
Yeah,
How much?
less than 4 volts left.
Something, yeah. It has to be the difference. Is that what you guys are saying, telling me? It's 12 minus 8.5, yes?
Yeah, 3.5.
So it's going to be 3.5 volt roughly, okay? So we know the voltage drop because again, it's like you are on the 7th floor and you went from the 2nd floor to the 7th floor, that's 5 floors. So now from the 1st to the 2nd, there must be only 1 floor. Or more from the, whatever it is, so it's going to be the difference, okay? So in this case, that is the 3.5 volt. So I know that the voltage from this end to that end is 3.5. So I can find the energy in here up front quickly because it's 1/2 of C, which is 3.5, times the 3.5 squared. So I get the energy in here. in a similar fashion, I find the charge in there in this section, because I can find now the charge in here too, because I have the voltage, which is 3.5 volt. Okay, and I know how much microfarads in here. So remember, the charge is equal to, what is it? Q is equal to CV, and C is 3.5 microfarads times 3.5 volts. And if I multiply this 3.5 times 3.5, should it be more than 26? Because overall charge is 26.4 microcoulomb. And when it came to this point, it split itself. Some of it went this way and the other some went up there. Now, can this charge be more than 26.4? Or that charge, for that matter, can be more than 26.4? Obviously, the answer is no. Because if you have 26.4 splitting itself between this charge and this charge, either of this charge cannot be more. Again, the conservation of charge in this junction. So if I do the product in here to find how much charge went to the bottom one, then it's easy. Then it's going to be, we're way outside of the problem, but it's really an important discussion that you guys really need to be thinking about when it comes to exam times, because you really need to do that. So again, 3.5 times 3.5, or 3.5 squared, it's going to be 12.25. So this is this charge in here. So it's 12.25 or 12.3 microcoulomb, okay? So if overall is 26.4, then this one must be 13 or must be 14.1 microcoulomb, so that if I add them up, it's 26.4. And then now I know the charge in here. Again, I do just 1/2 of this charge divided by this capacitance squared. Now I have the energy there. And the same charge, 1/2 of the same charge divided by squared divided by this capacitance. Now I have the energy there. So I have the energy here, I have the energy there, I have the energy here, I have the energy here, I have the energy there. All I have to do, add all of these energies, it should be exactly 158 microjoules. Sounds fun, doesn't it? Yes? What do you guys think?
Sounds tedious.
But that's what you do in circuits. I have seen so many of my students, once they start dealing with these things, they actually start thinking about becoming electrical or electronic engineer, because they see that all of these calculations, and actually it's kind of tedious, but at the end, exercise is rewarding. Okay, obviously when you do both of these majors, especially in electronics, you're going to be dealing with semiconductors and all the materials, but that's part of transistors and diodes and all kinds of things. Okay. Now, problem 53. So that was problem 51. Let's do 53. How are we doing on time? Still have time for the other problems. Okay, problem 53. It says you have a capacitor C1, C5 equal to 8.4 microfarads. C2, C3, and C4 are equal to 4.2 microfarads. The applied potential is 220 volts. That is like a European system. What is the equivalent capacitance of the network between points A and B? Calculate the charge on each capacitor and the potential difference across each capacitor. Wow, this sounds to be, this is the exact work that we were doing earlier with the other problem. So we have a point A and we have a point B. And here we have C1. And then I'm going to go all the way across to C3. Come back in here to, this is C5. Move across to C4. Looks like I have an H there. Hopefully you guys. And now I have a C2 in here. Okay. So this is what they're telling us. C1 is equal to C5 is equal to 8.4 microfarads. And then you have C2 is equal to C3 is equal to C4 is equal to C2 is equal to C3 is equal to C4, which is half that value, 4.2 microfarads. That becomes important, this connection between the values. What is the equivalent capacitance? Okay, again, the strategy is to look for the innermost. And the innermost is clearly this one. C3 and C4. And both of them are the same value. So if you do that, it's going to be simply their C equivalent. I'm going to write it in blue now. The C equivalent now between 3 and 4, I'm going to call it C34, is going to be 1 over C3 plus 1 over C4, the whole thing to the -1. Since both of them are numerically the same value, so it's going to be just 2 divided by either 1, 4.2, and the answer to the -1, and the answer is going to be microfarad. So 4.2 divided by 2, that's 2.1. When you invert, 1 over 2.1, when you invert, is going to be 2.1. So I don't even need a calculator for this one. So we have found C34. So now how the circuit look like? It looks like this thing doesn't exist now, no more. But I have rather a C34 now. If I look at my circuit now, the innermost are these two capacitances, C2 and C34. So I'm going to call it C234, okay? Except that they are in parallel now. So the only reason why I applied this result is because they were in series. C3 and C4, they were one after the other. So that's why I had to use this one. But now C2 and C34 are actually in series. So, in parallel, I'm sorry. So now their C equivalent between 2 and 3 and 4, I have to write a dash in here, is equal to basically the sum of the two, which is C2 plus C34. And for that, C2 is equal to 4.2, and the other one is just half that much. So this is going to be equal to 2.1 plus 4.2, which is 6.3 microfarads. So this is how the circuit look like now. Let me rewrite it now. Let me redraw it. So the points A and B are the same. Now this is C1. This is the C between 2, comma, or dash 3, 4. And now this is C5. Everything now is in series with one another. So the answer is going to be now the C equivalent now between A and B, as if this is basically what we really have. Okay, is going to be 1 over C1 plus 1 over the C between 2 and 3 and 4 plus 1 over C5, okay, to the -1, because everything is in series now. That's why I'm using this expression now. So it's going to be 1 over C1 is equal to C5 and is equal to 8.4. So, and both of them are equal to one another. So it's going to be 2 divided by either one. It's going to be 2 divided by 8.4 plus C234, which is 6.3. So it's 1 over 6.3, and the whole thing to the -1, and the answer is going to be microfarad. So again, 1 over 8.4, which is 1 over 4.2, and we're in business actually. So this is going to be 1 over 4.2. Since there is that connection between the capacitances, actually it could have been a lot easier than this calculation, but let's use the brute force still, to the power -1, and the answer is 2.552. So C equivalent is 2.52 microfarads. Please don't read too much to this number now, because I have a bunch of them that are in series with and a bunch of them that are in parallel. So you cannot really tell me that, hey, it's less than any of the smallest, so therefore it's kind of a series. No, it's a combination. But when you're looking at specific values, again, you have that. So we have that, okay? We have the C equivalent for everything. The question then is asked is to calculate the charge on each capacitor. The charge on each capacitor now should be, first of all, I know the overall charge, since I know C equivalent. Remember, Q is equal to CV. So Q total, which is the same charge actually on Q on 1 and 5. So that charge is going to be equal to, I'm going to call it Q1 and Q5 also, because that's the same charge. It's going to be the C equivalent times the voltage across A and B. And C equivalent is 2.52 times this, the voltage is 220 volts, 220. And the answer is going to be in microcoulomb, okay? So again, 2.25 times, come on, times 220, and the answer is 554. So Q1 is equal to Q5 is equal to 554.4, if you like, microcoulomb. Okay, so that answers Q1 and Q5. Now I need to find the Q on 2. For that, I need to find the voltage in here. That's one way of doing it, okay? I know that 554 split itself between these two sides. Part of it went to C3 and C4, and the other part went to C2. If I find C2, the charge on Q2, then it's just all I have to do is subtract it from there and I'm in business. Or I can check my answer again too, okay? So let's find the voltage in here. This voltage between here and here. Since I know the charge in here, now it's 554 microcoulombs. Since I know the capacitance, I know the voltage drop on C1. So V1, which I'm going to call it V1, is equal to Q1 divided by C1. And Q1, I just found it 554. Did I say 544? 554.4 microcoulomb divided by the capacitance of C1, and C1 is 8.4 microfarads. The micro and the micro cancel, and V1 has to be less than 220 volts no matter what. It cannot be more than that because the overall voltage is 220 volts. So this one is divided by 8.4, and sure enough, it's 66 volts. Okay, this is the same voltage actually on C5 because both of them have the same capacitance and both of them have the same charge. So this is actually V5 too. Now, if I go from here, I have 66 volts. And if I go from here to here, I have some volts. And if I go from here to here, I have another 62 volts, or I have 220 volts. So 220 volt must be this 66 volts plus this unknown voltage, which I'm going to call V2 now, plus the voltage on C5, which is another 66 volt. So the V2 must be 220 minus 2 times 66. So V2 now, they didn't ask me a V2, but I need V2. V2 must be 220 volts minus 2 times 66 volt. The answer has to be positive. It cannot be more than 220 volts too. So I'll have 220 minus 2 times 66. And the answer is 88 volts. So the 220 volt from A to B is actually 66 plus 88 plus 66, or if you wish, 66 plus 88 going around in here. It's the same 88 plus 66. It's the same voltage drop. So that is the voltage, but they didn't ask me for the voltage. They want the charge on Q2, on C2, which is Q2. Since I know what the voltage is, I can find what that charge is. So Q2 now is equal to C2 times V2, and C2 is equal to the other voltage, which is half the other value. C2 is 4.2 microfarads, and V2 I just found it. So it's 4.2 microfarads times the voltage, which is 88 volts, and the answer better be less than 554 microcoulombs, because that's the overall charge. The overall charge is 554 microcoulombs, and it split itself in part on C2 and in the other part, the same on both of them, C3 and C4. So this charge must be less than the 554. So let's check that. Q2 is equal to, what is it? 4.2 times 88. And sure enough, it's 369.6 microcoulomb. It's less than the 554. The 554 is sitting on both C1 and also C5. And only 396 or 369.6 is the one that is sitting on Q2. So how much is sitting on C3 and C4 in the same time is just the difference. So Q3, which is the same as Q4, must be the 554.4 minus the 369.6. And of course, the answer is going to be in microcoulomb. So all I have to do now is take the difference between my 554. Come on, only one. Minus this number. And the answer is 184.8 or 185 microcoulomb. Okay. Does this problem make sense to you guys? I know I'm very, very detailed and sometimes too much details, but I'm hoping if we go this way, you guys are at ease with these problems. You cannot learn this class. You cannot learn anything, as a matter of fact, if you don't go through these same steps and do them and write them yourself, okay? I can do them as much as you want in front of you guys and explain every single step, but if you don't do it yourself, you're not going to do this. So this is basically the item of the day today that you're supposed to check, verify, and calculate yourself. So at least at the end, you tell me that you did this and all of the numbers match, or there was an issue with that one, or that the one that you put in there was approximate. This is actually better, or the one that you needed to round, it needed to be rounded. This is how much it should be because of the sig fig stuff. Okay, that is part of the stuff that you're supposed to go through. All of these problems. Problem 57. We still have two more, and we have less time to finish them. Don't forget we have a lab later on too. 57. It says three capacitors having capacitance 8.4 and 8.4 and 4.2 microfarads. So C1 is equal to C2 is 8.4 microfarads, and C3 is half of that. Okay. Are connected in series across a 36-volt potential difference. So you take all of this and you put them. This is C1, this is C2, this is C3, and you put them across 36 volts, basically a battery or something. What is the charge on the 4.2 capacitor, micro capacitor? Which is the charge in here? It's going to be the charge on either of them, okay? It's the same charge everywhere. So I need to find C equivalent in here. And it's the same charge on all of them, okay? So for that, since all of them they're in series, so it's going to be 1 over C1 plus 1 over C2 plus 1 over C3 and the whole thing to the -1, okay? And since this one is equal to that one, so it's going to be 2 over 8.4, which is 1 over 4.2, plus 1 over 4.2, which is going to be just 1 over 2.1. And the answer should be, if you do the algebra, 2.1 microfarads. This is easy, because I'm assuming that you can do this one because you have 1 over 8.4 twice. So it's going to be 2 over that number, so which is 1 over 4.2, which is exactly this number. So now when you plug it everywhere, it's going to be 2 over this number, which is half of that value, which is 2.1. Now you're fully justified to ask yourself, is this value for the C equivalent less than the smallest of them all? And you're right in this case, because they're in series, it should be, and it is, okay? Because now you only have series configuration, no problem, okay? But they want not the C equivalent, they want the charge. So the charge now, Q, which is the same Q everywhere, by the way, is equal to C times V, and C equivalent is 2.1 microfarads times the 36 volts. So 2.1 times 36 volts is going to be 7.70 something point something. So 36 times 2.1, 75. Okay, 75. Whatever the calculator says, 75.6 microcoulomb. So that's how much charge is sitting on either one, any one of them. Doesn't matter which. Pick and choose. Since you ask for C3, that's the C3 because it's series, so they have the same charge for series. Okay. The voltage is the same when they are in parallel, though. But the voltage is not the same now. Okay. So we answered that part. What is the total energy stored in all three capacitors? Well, the total energy is actually the one stored in the equivalent. Okay. Since we know the voltage and we have the equivalent capacitance, then U total is 1/2 of C equivalent times the voltage squared, and 1/2.1 microfarads times the voltage squared, when that is 36 squared, voltage squared, that is. So the answer is going to be farads times volt squared, which is joules, but don't forget the micro. So this is a microjoule. So all I have to do is take 2.1 times 36 squared and divide that by 2. So the answer is 1,361 microjoules, or if you wish, 1.361 millijoules. Okay, so that is the total energy. So in this case, I did it because there was 1,000, which is just a milli. 1,000 micro is a milli. Okay, so this is how much energy is stored overall. And part C, the capacitors are disconnected from the potential difference without allowing them to discharge. They are then reconnected in parallel plates in parallel with each other, with the positively charged plates connected together. So basically, you take all of them, you cut them in here, this one, and this one, and you take the positive Q where it was positive, and you connect it in here, where the positive and you connect it in here, so that there is no discharge. And now you have this configuration. You have C1 in here. You have C2 in here. And you have C3 in here. So now this is the way that you do it, okay? Now, obviously, the voltage has changed. So you take them, you remove the battery, you built a charge. This is how much charge you put in every one of them. How much charge? We didn't calculate the charge, okay? Did we? No, we never did. The charge is going to be that you have it actually in each and every one of them is going to be equal to Q total, which is the same Q for all of them, is going to be basically equal to the voltage. Q is equal to C times V. I'm sorry, it's equal to, we calculated in here, 75.6. That was the question. Okay, very good. Thank you. This is how much charge is. So now imagine that charge is sitting on this capacitor and in this capacitor and this capacitor. And you disconnect the battery. So there is still charge. But when you rearrange them, now there is a redistribution of charge, that's all. So each one of them will get its own charge. So there will be a charge in here, Q1, there will be a charge Q2, and there will be a charge Q3 in such a way that the sum of the three charges is equal to, remember, it's going to be balanced in here in such a way it's equal to Q total. Furthermore, you have these voltages that are the same. So it's going to be Q1 over C1, because now the potential in here between this point and the point, on this side, it's Q1 over C1. On this side, it's Q2 over C2, which is the same as C1, by the way. So the charges on this side are going to be the same, is equal to Q3 over C3, okay? Which is half of the other quantity. So the charge is going to be twice in here. So basically, if I do this algebra, so there will be in here 2 Q of any side, plus the charge is going to be 2 on this one, again, to Q prime, that is, must be all to equal to the other Q. So the charge distribution will rearrange itself in such a way that this is how much charges you're going to have at the end. So it's going to be Q prime sitting on this one, Q prime sitting on this one, and this will end up with twice 2Q prime because it has a half capacitance. Solve this algebra. You have one equation, you have two equations, you have three equations, and the unknowns are Q1, Q2, and Q3, because you know Q. You know Q is equal to actually 75.6 microcoulomb. Once you find that, and you know C1 and C2 and C3, okay? Once you find that, you're going to find three equations, because you have three equations with three unknowns. Once you plug that, you're going to find the charges in here, okay? So I'm going to leave that to you guys, and hopefully you finish it. And if you have difficulty with it, you let me know, because we're looking for 10 minutes left and we have another problem. So this is a system of three equations with three unknowns. Once you solve that, you're going to find the charge. Which is it? What was the question? They are then reconnected in parallel with the positively charged plates connected to what is the voltage across each capacitor in the parallel combination. Okay, once you find any of these charges, you just divide it by the capacitor and capacitance of that place, and that is the same voltage everywhere. So that answers that question. So the question need to be found. First of all, find any of these Qs, which I called it Q prime, by the way, which is just a fourth of that Q. So it's going to be 1/4 of that 75.6 microcoulomb divided by the capacitance of C1, for example, and C1 was the 8.4, okay? Microcoulomb, okay? The microfarads, I'm sorry. So the micro cancels the micro, and you should finish the algebra and find how much voltage. It's the same voltage everywhere, because now they're in parallel. The voltage is the same. The chargers are not. The other way around in series, the chargers are the same and the voltage are not. But in parallel, the voltage are the same, the chargers are not, okay? So the chargers are not the same. They happen to be the same for Q1 and Q2. This two, because they have the same capacitance, that's all. This one has half the capacitance, so to end up with twice the charge. That's the only difference between them. Is it? Did it make it? Yeah, it should be that way, okay? Please verify the algebra for B, okay? Finally, what is the total energy stored now in the system? Now we're going to find the C equivalent. The C equivalent, since you find the voltage in here, the C equivalent is just the sum of all of the C's, which is just basically a sum of 8.4 plus 8.4 plus 4.2, so which is going to be 16.8 plus 4.2, which is going to be 20 microfarads. So the C equivalent now is 20, and now we're going to find the total energy, which is 1/2 times the C equivalent, which is 20 microfarads, times this voltage squared, okay? You'll be finding less energy. You should find less energy. So you ask yourself, where did the energy go? Again, you had so much energy in the system when they were in series. Remove the battery, it's still there. When you take them and rearrange them now, all of a sudden there is a loss of energy somewhere. And you need to explain where that energy went. Obviously, it did not go in thin air. Obviously, conservation of energy still works. So there must be a place for the energy to go, and that is actually leading to the next chapter, and it went actually to heating the wires. So when the charges started to rearrange themselves, they caused a current, and that current heat up the wires in here, and that is where the energy was lost, okay? So it went in the form of heat. But again, you need to not trust what I'm saying, calculate, and you should find that there is a loss of energy in here just by rearranging. That's all. Okay, problem 59. Still have about 6 minutes to do problem 59. Okay. So it says each capacitance C1. So now they give you a bunch of capacitance, but all of them, they are similar to one another. And they give you points A, B, C, and D. So let's draw this circuit quickly in here. So what we have. Okay, and then we have this wire in here, and then we have this wire in here, and we have this wire in here. This point is A, this point is B. And then what else do we know? We know we have capacitor C1 in here. Oops. We have a capacitor C1 in here. We have a capacitance C1 in here. We have a capacitance C1 in here. We have a capacitance C1 in here. We have a capacitor C1 in here. And we have a capacitor C1 in here. And finally, we have a capacitor C1 in here. All of them, they are C1 and they are equal to 6.9 microfarads. In addition to that, we have capacitor C2 in here. And we have a capacitor C2 in here in such a way that C2 is equal to 4.6 microfarad. Okay. Compute the equivalent capacitance of the network from A to B. Okay. The innermost is this one. There's three capacitors that they are the same value divided by the same value in here, C1. Since they are in series, it's going to be 1 over C1 plus 1 over C1 plus 1 over C1, which is 3 over C1. So I'm going to start working from the inside out. So that is, I'm going to call this one C1 equivalent, okay? It's again 1 over C1 plus 1 over C1 plus 1 over C1, the whole thing to the negative 1. So it's going to be really 3 over C1 to the negative 1. So this one is going to be C1 over 3. So whatever that value was, 6.9 divided by 3, and that should be the equivalent capacitance. So this is what the situation looks like to me now. It looks like I don't have this 3 anymore, but rather I have another capacitance, which is just this one. And this one is equal to 6.9 divided by 3, which is 2.3 microfarads. Okay? Don't forget, this is 4.6. Now 4.6 and 2.3, that is 6.9. Isn't that nice? 2.3 plus this capacitance, the blue one, which is 4.6, that is actually 6.9. So that looks like now I don't have neither of that too. I don't have this, but I have rather C1. So again, I'm down to C1 and C1 and C1, which is again 3 over C1 inverted, so it's going to be C1 over. So this whole thing then becomes also 2.3. Okay, and at 2.3 and 4.2, again, it looks just like a C1. So all of this up to this point in here is just like another red one. So I have a C1 and a C1 and a C1 now. Inverted, it's going to be a 2.3. So the C equivalent overall, without doing a lot of work in here, but hopefully you guys can verify it, the entire C equivalent is simply C1 over 3, or 2.3 microfarads. Okay? So we answered part 1. So you see how you work your way finding the answers? It requires a lot of algebra, honestly, but if you think about it, especially with the numbers that you're given, you're lucky enough to get this in the right numbers so that this becomes an easy manipulation, okay? So then compute the charge on each of the 3 capacitors nearest A and B. Okay, for this red one and this red one, that's easy because of the fact that, again, both of them have the same charge as the C equivalent. So now, how much the voltage they told us? Is 420 volt. So we have 420 volt, and we have the C equivalent 2.3. So we know the Q total, which is just 420 times the C equivalent. So again, 420 times it's 966 microcoulomb. So So this happened to be the charge on the first and the last of the ones that are immediately near. However, I need to find the voltage again, the same plan before. We know the actual voltage is 420 volt everywhere. So the answer has to be less. So I need to find this voltage on the first one. The voltage in the first one is given by V is equal to Q over C. So as we know what Q is, it's 966, and we know what C is 6.9. So the answer in here is going to be just 966 microcoulomb divided by 6.9 microfarads. So the answer better be less than 420 volts. So it's going to be 966 divided by 6.9, and that should be 140 volt. So there is 140 volt in here. There is a 240 volt in here, and we have the voltage drop in there. So what's the question? Is the voltage? So we found the charge with 400 crossing. Compute VCD. Oh no, I'm sorry. What am I talking about? Compute the and the charge on the we didn't. We need to find the charge. Okay. So the charges are 9066. So we need to find this charge on the next one, which is the blue one. For that, the blue one, in order to find the blue one, I have the overall voltage is 420. 420 deduct from it 2 times 140. That gives me the voltage across the 420. So again, 420 minus 2 times 140. So the answer is also 140 volt. So there is a 140 volt drop across the blue one, and the blue one has this much capacitance in it. So again, the charge on it, Q, is going to be just this capacitance, 4.6 microfarads times 140 volt. Now, it should be less than 966, of course. So we have 4.6 times 140 volt, and the answer is 644 on the blue one, not on this. This is the equivalent, okay, when we were doing the calculation. So on the blue one, there is 644 microcoulomb. So there is 966 on the first one, 966 on the last one, and 644 microcoulomb on the others. Now, they want this voltage here and there between C and D. We need that voltage, okay? Since we know the overall voltage is 420, and this voltage is 644, actually, I'm sorry, it's 140 volt too. So from point to A to point B is 140 volt. This voltage, now we need to find the charge that went in here, really, honestly. So we went above the time. Okay, let me tell you how you're supposed to proceed from here. You have options abound, okay? You have a lot of options when it comes to this point. You know the voltage is 140 volt across this blue one. You need to find the other voltage in here, and the other voltage is simply going to be also 140 volt across everything. But you need to find this voltage only, okay? Which would be less than 140 volt. So you need to find the charge that went in here. 644 went in here, but 966 came in here. So 966 minus 644 should be what? 966 minus. So, I'm sorry, 966 minus 644. So there is 322 microcoulomb went to this charge, okay? Which means there is another 322 went to this charge. So I can find the voltage now, since I know the charge, Q, which is 322 microcoulomb. I know the capacitance, which is C1. C1 times that one, that should be Q divided by this charge divided by this capacitance should be the voltage. So 322 divided by 6.9. So it's 47 volts. So 47 volts is in here, and 47 volts is in here. And overall, it's 144 volts between this side, okay? So 47 plus 47 deducted from 140, basically. 140 deducted from it 2 times 47. And the answer is 46 volts or 47 volts. Actually, it should be the same roughly number, okay? I rounded the number. It's actually 46.7. This is 46.7. And this too is actually 46.7. So the answer to the question is going to be 46.7, the last voltage. So again, you have a lot of options when you come to these problems to solve them because they're all linear problems, okay? You should be able to solve them. I hope, I know we went too far on some of these problems, but I hope that you guys understand enough of these problems to be able to tackle them and do them. If you have any difficulty, please let me know. Do not forget we have lab later on, okay? I'm going to stop the recording right now because we're meeting in less than an hour, less than 45 minutes, actually, a little over half an hour. And I'll see you guys, okay? Yes?
Sounds good. See you then.
All right. Thank you. See you.
You